Uh, Hello everybody, welcome to the second session on this course on Introduction to Machine Learning. So this week I will be covering decision trees. I will be explaining decision trees through a small example, and finally we'll move on to some questions, around 10 questions I think, on decision trees and linear regression. And so that would be how I'll go about today. And if you have any doubts in between, you can stop and ask me. Towards the end also, you can ask me questions on the topic that I'll cover, on the topics that I'll cover. So so decision trees. Let me see if I'm recording. Yeah, fine. Fine, yeah. So decision trees. So the main concept of decision trees comes from the fact that it's a tree-like structure. So you must have seen that in the lecture itself. So decision trees are called so because at every one of these points we take a decision, and they branch out, and therefore the name decision trees. So while in the course the decision trees have mainly been covered from a classification perspective, you must also keep in mind that decision trees can also be used for regression. Okay. However, for this course, the regression point of view of decision trees is not important. So I'll also talk about only the classification aspects of this particular algorithm. Some terminology. So the first terminology is the root node. So if you see here, the root, I have mentioned what the root node means. So the root node is basically getting some noise from somewhere. Can you please go on mute? Yeah. So the root node has arrows pointing out from them, but there are no arrows which are pointing into it. So people are still joining the class, and I have to go on admitting them. So the root node is one special node where it will only have arrows which are pointing out from them, but no arrows which are pointing into them. So that is the root node. And so coming from the root node, we will then go on to branches. So these green things, these green nodes, they are the branches, and branches will have arrows pointing towards them, and they will have arrows that are pointing away from them as well. So those are the branches. And finally we will have the leaf nodes. The leaf nodes are the exact opposite of root node, and they mean that the leaves will have arrows pointing towards them but not from them. So when we only have leaf nodes at the end, this means that the decision tree algorithm has stopped. And so that is the end of the decision tree algorithm, decision tree learning. Whatever you are doing has to stop when you get to leaf nodes. Now so there are many such things about how decision trees are built, how decision trees are learnt, and all those things. So the best way to show how decision trees are built or learnt would be through an example. So here I have taken one very simple example. It's actually taken from a YouTube. I found it from one YouTube from a YouTube channel. So let's say we have this condition. Of course, this is your target. And these are the three features that we want to talk about. So basically the question is, you have three movies, or rather you have two movies: Love's Titanic, Love's Lord of the Rings, and the age of the person. And you have to predict whether that person, given these three attributes, you have to predict whether that person loves Harry Potter or not. So that is the question that you are given. That is a setting that you are given, and these are your training examples. And let's say you have like So you have all different sorts of combinations. Remember that note here that the first two, like these two, they are categorical variables. So why categorical variables? Categorical variables are called so because they can only take values in a finite range, right? Right? I mean, they can only take values like yes, no. In this case, age is, however, a continuous value. Okay. In this case, age might be. You might think that age is 712, so it can only be integers. But you can go on to give ages like 7 point, which is 7 years 5 months, 7 years 6 months, and so on, in which case age becomes a real valued feature. And again, loves Harry Potter is because finally at the end of the day, as I said, that we will be talking about decision trees from the point of view of classification. We say that whether a person loves or does not love Harry Potter is our final prediction, is the final thing that we want to predict. So now how to build one simple tree. So this is the table. I have replicated the same table again here. So the first question that we need to answer is how to decide on the root node. So this is typically how you would go about if you create a tree by hand. Of course, if you use programs, then that program itself will do all these things and you don't need to worry about what is going on. But ideally, from a first course in machine learning, you should know how a tree is being made, how a tree is learned basically. So let's go about this. And if you have any questions, you can stop me and I'll be happy to take questions in between as well. So of course, now root node. So the first question is, of course, you cannot use Harry Potter because this is what you would predict. So you have three options here. You have loves Titanic, you have loves Lord of the Rings, and you have age. So these three are your candidate nodes. These three are your candidate nodes or candidate columns, let's say. Candidate columns in your feature matrix. These are the candidate columns on which one of which will become your root node, right? So let's see what happens if you choose the first column, which is loves Titanic. So loves Titanic, if it is true, then you need to so loves Titanic can either be true because yes or no. So basically loves Titanic true means yes, and loves Titanic false means no. Now you want to say that once you go on to this particular node, which means that you will now collect examples which collect only those rows which loves Titanic, and in that case how many of them love Harry Potter and how many of them don't love Harry Potter. That is the question that you are being asked here. So can one of you say what would be these numbers, these two question marks here? You are loving Titanic, but let's say you love Titanic as well as Harry Potter. What would be the number of, can you give me some numbers here? Okay, I don't, everybody is with me, right? Are you all confused about what I'm trying to say here, or? Yeah, I've got two answers, 1 and 2. Okay.
I think 1 is yes and 3 no.
Okay. Okay, let me again do it, because somebody answered 2 for yes as well. So see here, the question is, you are already in the loves Titanic region, so that means that you are in this, you have to consider only the rows which I am marking by arrow, right? So only these 4 rows you are marking by arrow, and out of that you see how many of them will love Harry Potter. So this is no, this is no, this is yes, and this is no. So this would be 1 and 3. You are correct, whoever said the answer was correct. So this would be 1 and 3. Okay. So and similarly, if you don't love Titanic, So if you don't love Titanic but you love Harry Potter, so now you are in these three rows. Yeah, now we are in these three rows, and here you would see that 2 will be yes and 1 will be no, right? So here this will be 2 and this would be 1. Can everybody please go on mute? Okay, I'll mute myself maybe. Yeah. Okay, so loves Harry Potter, and if you don't love Titanic but you love Harry Potter, that becomes 2 and the next one becomes 1. I hope they're correct. Oh, again this is yeah. So if you see here, these were the numbers that we had already got before in the last slide. Now that is one possibility of splitting on loves Titanic. Now let's say you want to see what happens when you split on loves Lord of the Rings. So if you love Lord of the Rings, so here I will mark the ones which are yes for Lord of the Rings. So this is yes, this is yes, this is yes, this is yes. So there are 4 yeses, and out of that 3 love Titanic. So here there would be 3 and 1, and if you have no, then that means and all of them are no. So if you see here, there is a direct correspondence between the no of loves Lord of the Rings and loves Harry Potter. So all the no's will go into this particular I mean all of them will be no, and only one, and there will be no yes left if you split on loves Lord of the Rings. So that is another way of splitting. Now there is a third way of splitting, right? I mean the third way of splitting is slightly more complicated. Like if you have so it will be based on age, and age is, I mean you cannot have these true false. If you are splitting based on age, you can't do this true false things. You have to do on the basis of something else. But okay, let me come to that yes, I mean let me come to that age bit later. Now let me give you one more terminology here. So this terminology is, these are known as impure leaves. Okay, why are these called, I mean these are all impure leaves, right? These are all impure leaves. Why are they impure leaves? Because you see that there is a mixture of yes and no. It is not like you have reached a decision concretely. You have got into, yeah, okay, yes is no is majority in this, yes is majority in this, yes is again majority in this, but you have the representation from the other class as well, and therefore these are called impure leaves. On the other hand, if you look at this particular leaf, this has no yes, only 3 no's, and therefore this is known as a pure leaf, because there is representation from only one class in this particular leaf. Okay, so so now we have created 2 splits. You have created 2 splits based on loves Titanic and loves Lord of the Rings, and now you want to see which one is better. Now see the first, so of course in the course, I mean in the lecture, I think entropy was shown as the method in which you select 2 of them. I mean you select both, which one you would split on. I am just for the sake of it, I mean just for some variety, I am showing the other index which was mentioned in the lecture, which is the Gini index, and so I would be showing that for this particular lecture. But of course you can Gini index and information gain, both of them can be used without any concern. I mean both of them will give you the same results. Okay, so right. So one way of doing this is, so there are many ways to so as I said, and many ways to calculate the impurity in leaves. Gini impurity, entropy, information gain, all those things are there. Now we'll talk about the Gini impurity. So Gini impurity, this definition was also given in the class. So the Gini impurity of a leaf, if there are C classes in the leaf, each with a probability of PC, then the Gini impurity is given by the following equation. So this is 1 minus summation of PC whole square. Let me give you an example, then it will become much clearer. So if you note, I mean if you look at my previous slides, you would also understand that when we are building the tree, and splitting on the basis of Love's Titanic, then on the left part we get this, we have 1 yes and 3 no, and by the formula of 1 minus sigma pc square, here pc is equal, c is equal to 2 because we have yes and no only. So so the probability of yes here is 1 by 4, the probability of no here is 3 by 4, and this is the Gini impurity. Okay, that is one. So we have got the Gini impurity of this particular leaf. Then we go on to, okay, okay, now we go on to the next node, this particular node, and here we have 2 and 1. And here if you see the Gini impurity, again by the same formula, here it would be 1 minus 2 by 3 whole square minus 1 by 3 whole square, it would be 0.44. So based on based on these two Gini impurity values, we need to find out the Gini impurity which occurs in the decision tree when we split on the basis of Love's Titanic, and that would be a weighted combination of these two. So what will be the weights? The weights would be the total number of examples that come into each of them individually. So here there are 4 such examples, here there are 3 such examples, and therefore we have 4 by 7 into the Gini impurity index of this particular node, which is 4 by 7 into 0.375 plus 3 by 7 into 0.44, which gives me 0.405. So this is one. So that means that if you split on Love's Titanic, then at the second stage, I mean just after the root node, the impurity that you get is 0.405. Now you do the same thing for Love's Lord of the Rings. So Love's Lord of the Rings, so we come here, right? I mean I am taking this one intentionally, the right one first. So can somebody say what will be the Gini impurity of this particular leaf? It's the same formula, right? It would be, the formula would
0.
0, 0.
Yeah, correct. So this would be 0, right? So the Gini impurity of this would become 0, and similarly the Gini impurity of this one would become 1 minus 3 by 4 whole square and something. So if you take the total Gini impurity, this would be 0.214. So the Gini impurity, when you would if you had taken the split to be Love's Titanic, it would be 0.405, and if you take the split to be Love's Lord of the Rings, it would be 0.214. So the Gini impurity is much lower in the case of Love's Lord of the Rings, and therefore this at least you know that between these two, this one is the one which you would prefer. Okay. So Love's Lord of the Rings is the one which you would prefer. You would have got a similar result. You would have got a similar result if you had done it from the information gain perspective as was shown in the class. You can check that for yourselves. Right. Okay. So now we come to the other question which I had postponed for some time, which is what you do when you have a continuous real valued feature, which is like age in this case. So here you can you can say that, okay, so all of a sudden how come you get this value age of less than 9.5. Now you will find many such ways in which you can actually find out where to split this particular value, but one of the easiest ways to do this is to take the midpoint of all of them. So what you do basically is you take this value, you take this real value, you sort them from the smallest one at the top, and at the so basically you sort them in ascending order, and then you take the midpoint of all these values. So the 7 and 12, the midpoint is 9.5, 12 and 18 the midpoint is 15, 18 and 35 the midpoint is 26.5, and so on. So you select all of these values accordingly. So now what happens is, so now you have got these many split points. So if you have 1 2 3 7 such values in the age column, you will have 6 such splits. Okay, so now you take each of these splits and you compute the Gini impurity index based on that. So the major concern here was how to get these splits. So that is solved very easily by taking the midpoint of all these values and taking that to be your split point. So I have, for example, shown the first split point. So let's say, I will rub this off, otherwise it might be confusing. Yeah, so let's say I have taken 9.5, which is the midpoint between 7 and 12. So that means that you have only one point in the true case, and all the other 6 values will come in the false case. So only one value is, which is no here, the Gini impurity is again 0, and and all these 6 values goes into this particular node, and they are equally distributed of 3 and 3, and the Gini impurity index is highest in this case, which is 0.5, and if you take a weighted average of them, it comes out to be 0.429. Okay, so
can you kindly repeat once more? This one little bit difficult.
Yeah, so you understood how I got this 9.5 value, right?
Yes, that is understood. But after that,
yeah, so now if you have age of less than 9.5, if it is true, that means you have only this particular row coming here, right? Only one age is less than 9.5, all the other are greater than 9.5. Okay, so here, and this person doesn't love Harry Potter, so therefore this is no, there is no yes, I mean 0 yes, 1 no, and all of the others, all these 3 will go into this particular node, and they are equally distributed between yes and no. So that is why you have 3 yeses and 3 no's, and the probability of that would be 1 minus half whole square, which is 0.5. So this is the highest value of the Gini index that you can get. And so the Gini impurity becomes 0.5, and again, like I had done before, the weighted average of them, because this has 6 cases and this has only 1 case, so it would be 6 by 7 into 0.5, which is 0.429. So the Gini impurity index, if you had taken the split of age less than 9.5, is 0.429. Is it clear now?
Yeah.
Okay.
So that will be repeated for the rest of the cases, right?
Yeah, so now it will be repeated for less than 15, less than 26.5, less than 36.5, less than 44, and less than 66.5. All of them will be repeated, and you will calculate the corresponding Gini impurity indices. Okay, so that is how you handle a real valued feature. And you see here the Gini impurity index is lowest for 2 cases. So the Gini impurity index for this case is 0.343, and this case is also 0.343. So these are the 2 values which are the lowest, and therefore if somebody told you that you have to split on age first, any one of these 2 values you can choose. That is your choice. You can choose either age less than 15 as your split point, or age less than 44 as your split point. From the point of view of the decision tree, it won't affect it won't affect you that much. Okay, so now we have got the 3 split points. I mean, for all the 3 columns we have got the corresponding Gini impurity indices. So Gini impurity Gini impurity value for Love's Titanic is 0.405, for Love's Lord of the Rings is 0.214, and for Gini impurity and for age is 0.343. And therefore you should always try to get trees which becomes more and more which becomes very pure from the beginning itself. That means your tree will be shorter. Okay, and therefore Gini impurity index, based on the Gini impurity index, you should always choose 0.214 or Love's Lord of the Rings as your split point. So that is what is shown here. So you have now split on love's Lord of the Rings. You see here that this immediately you don't need to split anymore, because you have already got no 3 and yes 0. So that means anybody who
How
doesn't,
Gini impurity, sir, for age is 3.43. They are different. Then you have chosen the lowest one.
huh?
That is the Gini impurity for on the basis of age. You have chosen 3.43.
No,
Means
it,
the lowest one we will choose, no, sir.
yes, we will choose. That is why I have chosen Lord of the Rings.
Okay.
Yeah. So now Love's Lord of the Rings, you see here that once you split based on Love's Lord of the Rings, immediately what you get here is you get 0 and 3. So this means that this has already become a leaf. You don't need to, or pure leaf rather. This has become a pure leaf, and you don't need to split based on that, because what will you do? Splitting on a thing which you have already, which is already giving you a clear cut decision. But this is impure, right? This is still yes 3 and no 1 and so on. So I mean, of course this particular case is very, I mean, is made up, and of course I cannot I mean for a longer example it would be very difficult to work it out by hand, and therefore this is looking like this. Generally it won't look like this. First stage you will almost never get a leaf, okay, I mean pure leaf. So now once you do this, then the next option is again here also. Hello.
Your voice was not audible.
Yeah, my yeah, sorry, my network connection got I got disconnected from the call, so that's why.
No problem. Can you explain that page once more? That the true false that is not very clear.
Yeah,
Just the last one.
let me see. Um,
Mr. Suraj just muted because there was some background sound.
yeah, my screen, and I am also audible, right? My screen is visible, right?
Yes, yes.
Yes. Okay. So yeah, where was I? Yeah. So you had a doubt somewhere, right? Can you tell
No,
me again?
no, the last one. You go ahead just before your network disconnected. The last one.
Okay. Okay. Yeah. So here, what you have done is you have already split based on Love's Lord of the Rings, and now you have got a pure node here. So this is a pure leaf, and then you have come to and now you can now split this particular node which has Love's loves Harry Potter 3 and 1. So now you can again try to split based on age or loves Titanic. So I'm showing here loves Titanic. I'll also show age probably. I'm not sure. I'll also show based on age once. So here basically what you are trying to do here is you take the cases which are you take the cases where loves Lord of the Rings is yes, which is this one, this one, this one and this one. These 4 cases, they love Lord of the Rings. And now you it's a very simple thing, right? Now you look at loves Titanic and again you look at yes here. So that is 1 and this is 1. Okay, so basically now you look at 2 cases. I mean this particular node corresponds to these 2 cases. Okay, why? Because they love Lord of the Rings as well as Titanic, and only these 2 cases are there where both of them are yes. And you see here that one of them is yes, and in the loves Harry Potter case, one of them is yes and one of them is no. Therefore yes is 1 and no is again 1, right? That is one case. The other case is when they love Lord of the Rings, that this is this particular case, when they love Lord of the Rings but they don't love Titanic. So that means those are these 2 cases, and both of them love Harry Potter. So this means again you have got a pure leaf here, which is 2 of yes and no is 0 here. Okay, so this is again a pure leaf. So this is how you can split a particular leaf which you have already got into 2 more, into a branch. You can convert this leaf into a branch in this way. The other way is now again you have to check based on age. So again you take age of 12.5. Why did I take 12.5? Okay, let me see. Okay, loves Lord of the Rings. So loves Lord of the Rings means yes, yes, yes and yes. So the ages now 7, 18, 35 and 38. Okay, so the midpoint of 7 and 18 is 12.5. 18 and 35 is 53, which is 26.5, and right, and 35 and 38 is 36.5. So these are the 3 age splits that you want to look at. Is this clear how I found this 12.5, 26.5 and 36.5? Yeah. Okay, so now you have taken this age of less than 12.5. Now you see a very interesting thing happens. Whenever you take this age of less than 12.5, I'll rub this off, otherwise this might get a bit confusing. So age less than 12.5 means only one person is there, right? Only one person is there who loves Lord of the Rings, and answer is no, which means that this becomes no. So this comes into this node. The rest 3, all of them, they love Harry Potter and they go into this node. So now you have ended up with 3 pure leaves. This is 1, this is 2, this is 3. All of them are pure leaves because you see only one representation is there. Okay, only one representation is there. One case it is no, one case it is all yes, another case it is no. So of course you can't, your tree has to stop at this point, because you can't go, you can't expect to have anything better based on this. However, it is a likely scenario. Of course in this case you won't understand it because it is a very small example, but it is a likely scenario where you have fit your training data perfectly. You see there is no case of wrong there is no one particular case where your model is predicting something to be wrong. Everything it is able to predict correctly from this table. So this means that your training error has gone down to 0, and this probably shows that you are overfitting. Especially the marker for this is, you see here in this case you have only one person who is saying no, right, and your leaf has become very pure. this is still fine because you have 3 examples where there are yes. So mostly this is a very strong feature on which you have split. This is also a strong feature on which you have split, but this is not that strong a feature because ultimately you have got only one example here, right? So if you have only one example of this sort, that means that you are fitting your training data very well and you are not likely to generalize to your test data, and therefore this indicates some overfitting that is happening in your decision tree, and therefore it's better that you don't grow the tree any further than this. So we already saw that if you can't grow this way. So if you grow this way, then the best split would give you the best split would give you this particular structure of the tree, and that I said that it is probably an indicator of overfitting. Therefore it's best to keep your tree at this point only. You don't need to grow your tree any further. Then what you say is, anybody who loves Lord of the Rings, so finally your decision is something like this: anybody who loves Lord of the Rings also will love Harry Potter. Anybody who doesn't love Lord of the Rings won't love Harry Potter. That is your final decision. So the first point is better to not grow the tree any further. Anybody who goes to the left branch is predicted to love Harry Potter, else not. That is your final decision tree, and that is and you stop at that. You don't move your tree any further. Okay, last final one point is, again as an aside, these decision trees can be used for regression. So where will the difference lie? The first point is, you take the split which minimizes the mean square error. So instead of the Gini impurity or the entropy or rather the information gain, you take MSE or the mean squared error. That is one. And the other is split on a particular variable, assign the average value of all points in that class. Somebody is asking, is there any link for the instructor notes? I believe you will get access to all these notes. Yeah. So assign points.
Last one is not yet received, I believe.
Oh, I have given it to the NPTEL people. I think they should be able to give the link. I have given actually a Google Drive link to them, so they will probably give it to you in some time. I don't know. I have already supplied the link to them. Yeah. So the first question is how you split. Instead of the Gini impurity, you take the mean squared error, and then you split whenever you split on a particular variable. So like here you had taken yes 3 and no 1, and yes 0 and no 3, and you are moved ahead based on that. Here what you will have is, instead of yes and no, you will have some values, right, because of regression. So you just take the average of all those values, and that becomes your node value. So yeah, so this is an aside. This won't be asked in your exams also, and this is not part of this particular offering of machine learning course, and therefore I won't go into much more details about that. So if you have understood this example, then it's fine. I'll just go through some 5 or some 10 questions now. So if you have any questions, you can ask me based on this example. Otherwise I will move on to the questions. Okay, I think this is clear for everybody. So I will now move over to some questions. Let's see. Yeah. So this is actually some questions I have taken from another course on machine learning, which is offered by NPTEL only. So these are some MCQ questions. I believe I have some 10 of them. So we'll solve them. These will be simple only. So yeah. So let's go ahead with it. So the first question is, and I would ask you to give I would ask you for some answers for all these questions. So if you have answers, if you are not sure, even then you can just say. It's better for me to also to clear your doubts that way. Okay, so the first question is, which of the following properties are characteristic of decision trees? So first is low bias, then is high variance, then is lack of smoothness of prediction surfaces, and unbounded parameter set. So can somebody say whether decision trees suffer from low bias or not?
Low bias.
Right, so this is definitely correct. Anybody has any questions about why it suffers from low bias can ask me. I can tell it to you now. But let me go through this question first. Then high variance, do decision tree exhibit high variance?
No.
Okay, no. So let me give you the example of which I just went through. So there we had some 7 examples training, and if your decision tree, so the first thing that you have to assume in such type of questions is you are not using any validation set, you are not pruning your tree, you are not doing anything to the tree, you are just letting it run on its own. So you saw in this 7 examples case that finally it led to a training error equal to 0. So so as I mentioned in the last class also, what does a training error of 0 signify in terms of, let's say,
Overfitting.
correct. So whenever it overfits, that means bias is low and variance is high. Okay, so decision tree is one of those algorithms where they suffer from low bias and high variance. So what it means is, if you let the decision tree run on its own, it most likely will find out a way to reduce the training error to close to 0, may not be exactly 0 but close to 0, but in that case your test error would increase. Okay, so that is one of the features of decision tree. And the other is lack of smoothness of prediction surfaces. So this probably is not part of this course, but okay, see, so let's say your decision tree, you had values like x and y, okay, and they are both real valued. Okay, so it is like 2, 3, 4, 4.5, 5, and this has values like 1, 2, 3, 3, 1. Okay, so you have, so this is your entire space where you are operating at. So this is x and this is y, and z is, let's say z is your decision variable. Z is some yes, no, maybe yes, no, yes, yes, no, something of this. So this is just a random example. So you see here, and your decision tree comes up with a condition like z will be yes, let's say, if x is less than okay, let me make it even more complicated. Suppose your decision tree comes up with a condition like z equal to yes if x is greater than 2 and less than 3.5, and y is between 1 and 2, let's say, something of that sort. Similarly z, so what happens here is x is between 2 and 3.5, so let's say x is 2 and 3.5, and y is 1 and 2, so y is 1 and 2, so this region would be yes, let's say, and you might have another region like this which comes out to be yes. I mean, decision tree can give you such sort of things, where this becomes yes, this becomes yes, this becomes no, again this becomes no. I mean, okay, I will shade it differently, maybe it might be, this will be confusing. So these are all the no regions, these are all the yes regions. Again, this is a, let's say, yes region, and this entire thing is a no region. So you can understand, right, that you can get these sort of conditions due to which these sort of decision surfaces might come up, and therefore this decision surfaces, as you can definitely see, these are not smooth. These are all some brick wall sort of structures, and therefore the decision trees will lead to prediction surfaces which are not smooth. Okay, I hope this point was clear. I know that this was not taught in this particular course, but just remember that decision trees don't have very smooth prediction surfaces. Okay, then comes now this is an important thing. Okay, what do you mean by unbounded parameter set? So unbounded parameter set means, for example, I mean, of course, linear regression was also taught to you all in this particular week. So there we had something like beta 0 plus beta 1 x plus beta 2 x square plus beta 3 x cube and so on, right? We had something of that sort. Now here you see these are all parameters, beta 0, beta 1, beta 2, beta n up to dot dot. Let's say if somebody asked you to move up to beta 1 lakh, you moved up to beta 1 lakh, and that becomes so you have 1 lakh parameters in this case. You have 1 lakh parameters in this case. However, you saw in the example that I showed you and also in the course, we did not talk of parameters at all in decision trees, right? We were just looking at, okay, what are the split points? This is a split point. Okay, what is the gene impurity index? What is the information gain based on this particular split point? Okay, this is the best split point, just split and go ahead. So at no point of time we are actually bounded, or we are actually talking of parameters in the decision tree. Therefore decision tree is one of those special machine learning algorithms, they are very rare to find, that you don't need any parameters at all for representing a decision tree. You just require a set of nodes and a set of conditions. Based on that you will be able to define your decision tree. You are not looking at parameters. So in this particular case, all these 4 points are characteristics of decision trees. They suffer from high variance, they also have low bias, their prediction surfaces are not smooth, and they are not bounded by any number of parameters. Okay, right. So let me go to the next question. So here we have a small example. So the example is, and this looks at the entropy and the information gain. So I thought of putting this example because entropy and information gain was what was taught in the class. Okay, so the first question is, there are 2 questions linked with this particular data set. So the first question is, what is the initial entropy of malignant? So malignant, if you see here, so there are what 1 2 3 4 5 6 7 8 12 examples. Out of that 1 2 3 4 5 6 7 are positive, 7 are 0 and 1, and remaining 5 they are 1s, and the entropy would be minus 5 by 7 log of 5 by 7 minus sorry not 5 by 7, very sorry, because there are 12 examples. 5 by 12 log 5 by 12 minus 7 by 12 log of 7 by 12. So and these are all log base 2. Okay, so of course I won't be able to do this calculation. The answer that would come out to be is 0.9798. You can check that for yourself, and this answer would come out to be 0.9798. So this is pretty standard. I mean, if you remember the formula that was given in the class, it is minus p plus log of p plus minus p minus log of p minus. So here p plus is 5 by 12 because out of the 12 examples 5 are positive, and p minus is 7 by 12, out of the 12 examples 7 are negative. So that is another solution, that is another question. Now linked to this same question, we have for the same data set, what is the information gain on vaccination. So that means that from this example, if you now split based on vaccination, then what is the information gain that you get. Okay, so the first thing that we need to note here is malignant. The entropy of malignant was 0.9798. Of course, I did not show this, but you can calculate it for yourself. And now you need to split on vaccination. Okay, so let's say this becomes your root node. Now you have
Sir,
done.
please show us question 2 so that we can take a screenshot of that one, sir.
Yeah. I'll come again. I'll show that again. Okay. I myself need to look at that. Yeah. So this is the particular thing. So now you see vaccination, if it comes out to be 1, so I will put an arrow here. Okay, I will put an arrow here. So vaccination, this is 1, this is 1, this is 1 1 1. Okay, and rest all are zeros, I believe. Yes, so there are 5 ones and 7 zeros. Okay, so now we have vaccination. Yes, first let me go into that part of the decision tree where vaccination becomes 1. Vaccination takes a value of 1. So this means vaccination equal to 1, and this is vaccination equal to 0. Now out of the vaccinations which are equal to 1, all of them have a malignancy of 0, right? All of them have a malignancy of 0. So that means malignant is 0, not malignant is 5. Okay, I hope I am doing things correctly. Malignant is 0 and not malignant is 5, right? Now you have another case where now we are going to the right part of this particular decision tree, where you are taking a vaccination of 0. So vaccination of 0 means these cases. So of course you have 7 cases, and out of that you have 0 in these 2 and 1 in these 5. Everything is clear, right? I mean, you guys are all with me, right?
Yes.
Yeah. So here malignant becomes 5 and not malignant becomes 2. I hope I did correctly. And not malignant becomes, yeah, not malignant means malignant 0 I am putting as not malignant, and malignant 1 I am putting as malignant. Okay. So now you need to calculate the entropy for both these cases. So here there were 12 cases. Now this has 5 cases, this has 7 cases. So the entropy for this is pretty simple. It's
0.
Precisely. So it's 0. So I'll just calculate, because otherwise it might be confusing for somebody. So right. So this is, again I am taking this formula of minus p minus log p minus p plus log of p plus. Okay, so that becomes minus negative. Negative is malignant not 0, malignant 0, which is 0 by 0 log of yeah, so this becomes 0 into infinity, which is basically 0, and this is 5 by this is 0, this will be 0 by 5.
No, 5 by 5.
This would be 0 by 5, and this
5.
would be 5 by 5 and log of 5 by 5. So this again becomes 0. So the entropy of this becomes equal to 0. Okay, this part is done. Now coming to this part, here P negative is 2 by 7, P positive is 5 by 7. Therefore, the formula of this would be minus 5 by 7 log of 5 by 7 minus 2 by 7 log of 2 by 7. So this becomes your this becomes the entropy of this particular node. Now so here the entropy was 0.9798 at this particular stage, and here after splitting on vaccination, I again don't know what this value is. This value, let's say I am calling it to be EV. So your information gain would be IG would be 0.9798 minus, so the first thing is this is anyway 0, but if you had written it, so it would be 5 by 12 into 0, because you are taking a weighted average of these two nodes, minus 7 by 12 into this EV. Okay, whatever this EV comes out to be, you multiply it with the total number of samples by that you multiply it with the probability of a sample ending up in this particular node, which is 7 by 12, and you multiply that with the entropy of that, and that is the total entropy at this particular stage. Okay, this is the entropy of this particular stage. You already had the entropy of 0.9798 before. You subtract these two entropies and you get the information gain. That is how you calculate the information gain. I can check once, but I think it would be 0.4763. That's what was written in the answer. So I think it is 0.4763. Okay, is this clear to everybody?
Just I think I missed something.
Yeah.
How did we get this entropy of malignant at 0.9798?
Oh, that is the calculation. I mean, that I did not go through. So that is minus 5 by 12 log 2 of 5 by 12.
Okay.
Yeah.
Got it.
Yeah.
Got it. Okay.
Yeah. Okay. So yeah. So the next question is an assertion reason type of question. So the first thing is, decision trees are linear non-parametric models. A decision tree may be used to explain the complex function learned by a neural network. So I'll come to the second statement. Second statement, I don't think it is. I mean, you would be able to answer this also, but the first question, can somebody say whether this statement is true or false? Decision tree are linear non-parametric models.
Sir, it's true because it is not a parametric model.
You are correct, it is not parametric, but is it linear?
Not sure, sir.
Okay. Well, can anybody try? Somebody is saying no. So see, I had shown a decision boundary here, right? So if your, let's say if your decision boundary is something like this, it is piecewise linear, but it is not linear, right?
Yeah.
So it is not a linear model. Decision trees are not linear, but they are non-parametric. So the first statement is definitely false. The other thing which I wanted to tell you all, which was not, I don't think it was shown also in the course. Now nowadays what happens is, deep learning and this machine learning, I mean machine learning is okay, deep learning, I mean the neural networks, all of them, all these models, they are the de facto standard for most of the works that we do today. Okay. However, these models have become black boxes in the sense that we don't know why they predict what they predict. Okay, we just feed in data and we get outputs. If the accuracy is good, we are happy. If the accuracy is bad, we again go on to train the models. We don't know why these models fail, or why these models say what they're saying. However, if you look at the basic way the decision trees have been designed, you would see, for example, in the case which I showed, in the worked out example which I showed, there you could come up with statements like, your final statement would be something like this: this person loves Harry Potter because he or she loves Lord of the Rings. Now this particular statement is something that we are all after. There is a huge branch of research in machine learning going on till date, which is known as explainability of machine learning, and that is the thing that we are trying to solve. That you say why you have predicted that this person will love Harry Potter. For decision trees, the way they are created, it's very obvious that they would be able to answer such questions. You just go from the root node. You go at the root node, you take a yes, then you take maybe another turn, I mean whatever turn that the particular test sample had taken, and at every point of time you say that okay, whatever this was, if this is yes, then that person must have loved this, that is why it has come to this particular node. The person must not have loved this, that is why it has come to this particular node, and so on. So decision trees, by the very way they are constructed, are very explainable models, and therefore decision tree are used to explain the complex function learned by a neural network. Okay, it can be shown, and I think it has been shown also, that decision trees are able to understand neural networks. I mean not the deep neural networks that we use today, but some deep neural networks, at least decision trees can learn very well. They can understand those or explain those neural networks very well. So here for this particular question, it is like the statement 1 is false because it is not a linear model, but statement 2 is true, as I just told you all. These are many, I mean I am giving some, I am making some statements which may not be required for you for this particular course, but it's better to know that, it's better to know all these things, that is why I am including them. And the next thing is, which of the following is or are major advantage of decision trees over other supervised learning techniques? So theoretical guarantees of performance, of course no supervised techniques can give you, I mean there will be some maybe, but at least decision trees, they will not give you any theoretical guarantees of performance. Higher performance, again you can have neural networks which will give a higher performance at decision tree, therefore it is not especially an advantage of decision trees over other supervised learning techniques, because other techniques can have higher performance. Interpretability of the classifier is definitely one. Okay, they lead to very highly interpretable models, as I also said in the last question, and more powerful in its ability to represent complex functions. Again this is not true because neural networks are more powerful than decision trees. So interpretability is one of the key reasons why we still think about decision trees today. Okay, so I think that was the last question. No, okay. So the last question is on decision trees. So the last question is, consider a data set with only one attribute. So it is a categorical attribute, and suppose there are q unordered values in this attribute. How many possible combinations are needed to find the best split point for building the decision tree classifier? So like I said, so suppose so there, I mean in the example that I showed, there I was only looking at yes and no. Here you are actually looking at q unordered values. Okay, so the q unordered values, an example can be color. Okay, so this is a categorical variable and there can be, let's say, 3 colors: red, blue and green. So how many split points do you need to look at? Based on how many split points do you need to look at in order to find out what is the best split point for the decision tree classifier? So let's say I will not go, I will use this 3 as an example, but let's try to derive this q from this q general values in itself. So let's say I have the features, right? So I have f1, f2, f3 up to fq. Okay, remember one more thing, the decision tree only makes binary splits, which means that you have to combine these features in such a way that they lead to only 2 splits. So for example, if you have color here, if you have color here, so you can only have 2 outgoing arrows, you cannot have more than 2 outgoing arrows. That is the condition that has been given to you. So F1 up to FQ is there, so they can, so both, all of them can either go into the left one or the right one. That is the only option. So I am denoting left and right by 0 and 1. So all of them can take either value 0 and 1 and so on. So there will,
one doubt here.
yeah,
Now that F, whichever you said, they are the values, right, sir? Because there is only one feature here. Attribute is 1.
yeah, attribute is color, so that is referred to by F, and red, blue, green,
Oh,
they
F
are the,
and to F. Those are the values.
yeah, those
of
are
that
the
feature.
attribute, they are the q unordered values. Okay,
Okay, sir.
yeah,
Sir, one doubt.
Yeah.
What split can it be still again? That L and R.
yeah. So now the other condition is the decision tree only makes binary splits. Like cart, you forget, this one you don't need to know, but the decision tree only makes binary splits. So suppose you have color which have red, blue and green. So you, since you can only make binary splits, you can only make them into, you can only have 2 such arrows, right? Because you will be splitting into 2 groups.
Yes, sir. So we can group red, blue in one and green in the other.
Correct, exactly. So I am just denoting them by left and right.
Okay, sir.
I am just denoting the groups by left group and the right group. That's all. And this left I am again denoting by 0, and this right I am denoting by 1. That is for ease of representation, nothing else. So this is basically LR, LR, LR and so on. Am I clear, or too much symbols and all those? Too many symbols I am using maybe.
No, no, sir.
Yeah, okay. So if it's clear, then I'll go ahead. So all of them can either be 0 and 1, and therefore this becomes 2 to the power q, right? Because all of them can take 2 values, and there are q such values, and therefore 2 to the power q. However, you see what happens is these two things are equivalent, right? 0, 0, 0. So the first q by, suppose q is an even number, the first cube half is all zeros, next are all ones, next q are all ones, and you have got another split where all the first q's are ones and all the rest as, and all the remaining q's are 0. These two are equivalent. Am I correct?
Just not understood.
Okay. So you have to understand here, like I mean the thing that you have to understand here is, see, these are all values, right? These are all values of the categorical variable that you are talking about. Now the first case here shows that the first q by 2 values, let's say you have 4 values, okay, let's say, okay, let's take red, blue, green and yellow. These are your colors. Okay, now if you split, so the one possible split is you put red, blue together and you put green, yellow together. Now it doesn't matter whether you put this onto the right or to the left, or you, if this is to the right, then this becomes to the left, if this is to the left, this becomes to the right. Am I correct? Is it clear now?
Okay.
Yeah, so so in this case what happens is, if you, it doesn't matter if you put red, blue here or here, provided red and blue are always together. Similarly, green and yellow, it doesn't matter whether you put on to the left or to the right, provided that green and yellow are always together. I will show you an example, maybe it will become more clearer after that. So this is like, I mean, we used to solve these sort of problems in permutation combination sort of settings, but yeah, probably I will make it more clear with an example just in a bit. So let me just rub this, and right. So because 0 0 I mean, okay, so because of that there will be 2 to the power q by 2, that is 1. Okay, just take it from me now. I will come to this example a bit. I mean, I'll show why this by 2 has to be there. And the other example is all of them is 0. There will be one such case, one such combination where all of them would become 0 or all of them would become 1, and you have to subtract that also, because that means that you have not taken any split. Whatever color was there, you have just moved on to the next part of the tree without splitting them at all. So you don't need to consider that. Therefore the answer for this would be 2 to the power q minus 1 minus 1. Now why this 2 is used? Okay, let me go to the end of this. I've kept some extra pages this time. So as I was saying, let me take the example of 3 colors. That would be easy for me. Red, blue, green. I am taking 3 colors. Okay. I am showing you splits. Now all the examples which have colors like red, blue are here, and all the examples which have green color are here. This is one possible split. The other example is color which is red, blue, green. Green comes to the left and red, blue comes to the right. Now can somebody say whether I should consider both of them separately or both of them are same?
Same.
Yes. So here if you see, I had what? I had denoted right by 0 and left by 1. I mean, all the features which went on to the right were denoted as 0 and all the features which went on to the right were denoted as 1. And red, blue, green. So this combination becomes 0 0 1. What does this combination become? Can somebody say? Like this became 0 0 1. What does this combination become?
0 1 1.
0.
0
1 1 0.
No.
0 1 1.
1 1 is
1 0 0.
1 1
1
0.
0 0.
It's
No,
1
1
1
0 0.
I'm getting many answers. So
Sir,
I
it's
think
1
1
1
0
0.
0.
okay, let's take the last answer which was said to me, which was 1 0 0. So what does 1 0 0 mean? 1 0 0 means that red has gone on to the left,
Side.
right? Is it correct? Has red gone on to the, oh, I this one only I have written wrongly. Somebody should have corrected me. Oh,
0 0.
yeah, this would be 1 1 0 actually. I'm sorry. See, red is to the left and left I have denoted by 1. Therefore red is left, blue is left and green is right. Therefore this is 1 1 0. So now can some,
Left.
0 1 1.
Sir,
okay,
it is 1 1 0.
now it is somebody
The
saying
right
me
is-
0
right
1
is-
1.
Okay, right is 0. You change the convention, that's why, sir. Left we always take a 0.
Okay.
And
Let
right
me
is-
let me write it in that way only. That might be easier. Sorry. Okay. Left is 0 and right is 1. Depending on that, what is red, blue, green in this case? It is 0 0 1. And what is red, blue, green in this case?
0 0 1.
No, in this case, this particular case.
Green.
0
1
0 1 1.
1 1 0.
0 1 1.
It is 0 1 1.
0 1.
1 1 0.
Okay. Somebody is saying 1 0 1 1 and somebody is saying 1 1 0. Okay, let's see.
1 1 0.
Yeah, so when somebody says 0 1 1, that means that red has gone on to left right? I have written this RBG, so left has gone on to red has gone on to left, which is not the case. Red has actually gone on to the right. So it is actually 1 1 0. Now we have got two different sequences. One is 0 0 1, one is 1 1 0. But from the point of view of decision tree, from the example which I showed earlier also, are these different, 0 0 1 and 1 1 0?
Yes, it is different, sir.
Okay, now why?
The values are different.
Values are different. Now when you are talking about split points of a decision tree, what would you what would you calculate at this point of time? At this point of time, what would you
Sir,
calculate?
leaf no more.
You would calculate the
Calculate entropy or
I
give
think both are
index or
same
entropy.
because
right.
both are same because in both decision tree, red and blue are together and green is separately. So I think the both decision tree are same.
Precisely. So here you see the decision tree at this point, of course the entropy of both of them is same. This much is evident, right? I mean at this point all of them are together, so entropy of both of them are same. Now this particular decision tree, if you take this entropy and this entropy, can they ever be different? This entropy and this entropy. The same number of examples will come into this node, the same number of they will be same, right? And
Yes.
similarly these two will also be same. For the green node also it will be same because they will have the same number of examples. And because of that, if you choose, if you calculate the split point, if you calculate the entropy for any one of these trees, you don't need to calculate the entropy of the other tree. Is it clear now? Because both of them will give you the same values.
No, sir. Yes.
Yes, sir.
So that is the reason why 0 0 1 becomes equivalent to 1 1 0. Now if I take three values, then of course you will find the there can be 8 possible values because there can be 2 to the power 3 values. So it would be 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. These are the 8 possible values, right? This is clear. Now I will talk about the first and the last values later. 0 0 1 is same as 1 1 0. 0 1 0 is same as 1 0 1. 0 1 1 is same as 1 0 0. So you only need to check half of these values. You don't need to check all these values. Again, you don't need to check, if you have already checked 0 0 0, then you don't need to check 1 1 1. Therefore you only need to check 4 values out of 8. Then again you don't need to check 0 0 0 because 0 0 0 means you have put red, blue, green in the same basket. So there is no point in checking that, and therefore out of 2 to the power q values, because of this symmetry you are dividing it by 2. Then you are removing the first value, which is all zeros or all ones, whatever, and you are subtracting it by 1. Is this clear now?
Yes, sir.
Yes, sir.
Okay, great. Where was I? Okay, this question. Then some simple questions on parameters obtained in linear regression. So the parameters obtained in linear regression are strictly, of course they can take all values in the real space. Okay, I should have asked somebody to answer me this, but okay, anyway. So basically you are not constraining linear regression in any way, therefore you are taking it can take all values in the real space. So that is a feature of linear regression. Okay, so this I will ask. This is also a very simple question. Now suppose we have n independent variables x1 to xn and the dependent variable is y. Now imagine that you are applying linear regression by fitting the best fit line using the least square error on this data. You found that the correlation coefficient for one of its variables x1 with y is minus 0.005. So which one do you think is correct? Regressing y on x1 mostly does not explain away y. Regressing y on x1 explains away y. Given data is insufficient to determine if regressing. So what do you mean by explains away y? Which means that how much dependence y has on x1 basically. That is what you are trying to mean by this question. So what do you think? What does a correlation coefficient of minus 0.005 indicate?
A, I think A.
Yeah, you are correct. So because the correlation coefficient is very low, the dependence of y on x1 is extremely low. Because of that, just by regressing on x1 you won't be able to find out, you won't be able to explain y probably. Y is not overtly dependent on x1. The fourth answer is this: regressing y on x1 mostly does not explain away y. Okay. Oh, then we have two more questions. Then we have an example about we have example about how to solve for linear regression. This is again a simple problem only. It should not be much difficult, I feel. So consider the following 5 training examples. We have 5 x values and 5 y values. We want to learn a function fx of the form ax plus b, which is parameterized by a and b. Using mean squared error as a loss function, which of the following parameters would you use to model this function to get a solution with a minimum loss? So you have to find out ax and b. Okay, yeah. So a and b you have to find out. So it becomes like ax plus b or y minus ax plus b whole square. That is the loss that has been asked, right? Mean square error loss. So I'll do that. So okay, these values will be are so good, is it? I mean, I don't know whether this question is correct or not. Anyway, yeah, y minus x plus b whole square, which is y square plus ax plus b whole square minus 2y ax plus b. Okay, so these are your values. So what you need to, okay, let me break it down further. Y square plus a square x square plus b square minus 2abx minus 2axy minus 2by. This will be plus 2abx.
That is a plus.
Yeah. So now what you need to find out? You need to find out, oh, this would be like okay, I have to sum it up for 5 examples. The value is like 8.6 and so on. Okay, let me see. This is 2, this is 3, this is 4, this is 5, this is 6, this is 5. Okay, this is something 7, 8.6, then 3, then 11.5. I needed a calculator for this. This might be difficult to get anyway. Okay. What can I do? I need to take a derivative of a, right?
There is no simpler way to solve this, sir.
No, I don't. I was checking that. This is okay. Let me see. I mean, there might be a simpler way. I mean, I don't even know whether the answers will be this good if you solve this properly. So that is what I'm thinking, but let me right. Let me see. Oh, so 2 maps to 7, 3 maps to 8.6, 4 maps to 3, and 5 maps to 11.5. Okay, the options are 1, 4, 4, 3, and okay. So one way would be to see which one gives you the minimum error, but I don't know whether that would be at least easier than trying to solve this and get, because I don't think this would be the correct answers. I mean, there would be some decimals. That's what I feel. It wouldn't be so good probably. So that is why I was trying to draw this line also. Okay, 3 plus 4.
We can put those values, get the value of fx, and then take difference and then
That is one way. I feel it would come to 3 4. I am not sure. Let me do it in that way only. So if I take that, also will involve some calculations anyway. So if you have 3 4, then that means this value becomes a and b, right? A and b, yeah. So this value becomes 10.
10.
Yeah,
Yes.
then this becomes 13.
13.
These become 16. This becomes 3 into 5, 15, 19. This becomes 22. I hope I'm correct. 10, 13, 15, 16.
Sir, how did you get this, sir?
Yeah, I'm just
You
putting
just the ax plus b, okay.
yeah, I'm just putting these values, because otherwise it's very 5 values with these dangerous things. It's difficult for me without calculator. So the error for this would be 3, the error for this would be 4.4, the error for this would be 13, the error for this would be 7.5, and the last one has no error. So this probably won't be the case. Then let me check.
I think 1 4 will
1 4, is it? Okay, let me see. So this has these many values. I'll just write these here.
Average of that, sir.
Yeah, I'll just write these, because just looking at this maybe will give us an idea. So if you have 1 and 4, then it would be what, 6. This would be 1 and 4, right? So this would be 7. This would be 1 and 4 again, so that would be 8. This would be 1 and 4, which is 9, and this would be 1 and 4, which is 10. I hope I'm doing things correctly. 1 and 4, yeah, this would be correct, because 1 and 4 means it will only increase by 1 for every case. 4 is constant, so 2 would give me 4. Yeah, this is fine. So the error here would be 4. No, the error here would be 1, then it would be 1.6, it would be 5, it would be 2.5, it would be 12. I still don't think it is the one which will work out. Let's check 4 3. 4 3 I'm writing here. 4 3 would be 11. 4 and 3. Yes, it would be 11. Then this would be 4 and 3. This would be 15. 4 and 3, it would be 17. No, I'm doing something wrong.
This is 19.
I think so, yeah. I write up everything anyway. Yeah, this would be 4 into 2 plus 3, which is 11. 4 into 3, 12 plus 3, 15. this would be 19, probably the next one would be 23, and the last one would be 27. So the error would be 4, then this is 8.6. okay, so this is 6.4, this is 16, this is 11.5, and this is 5. okay, so the last one left is, as of now, okay, I think 1.4 would be the correct answer. Probably 1.4 would be the correct answer. Okay, 7.5, 13 is 1, 7.5, 5 difference is there, 2. Yeah, that's what I feel. 1.4 would be the correct answer. I'll just check this once and I will solve it by myself, and I will commit to the next. I will tell about this. I mean, this is quite simple. It's just that you need to do a lot of calculation. So yeah, so without a calculator this might be, I mean, there will be mistakes here. So probably 1.4 is the correct answer. Okay, so I'll move on to the next one. The next one has, I think, has some error. So the question would be the relation between starting time in hours and grade on the final examination in a random sample of students in the introduction to machine sum class is this. So here Ax plus B has already been given to you. How will a student's grade be affected if she studies for 4 more hours? Okay, so the student has increased the studying by 4 hours, and it's simple that, so therefore the grade probably would increase by 60.8 points, because 15.2 into 4, which is 60.8. yeah, this is a simple straightforward question. Yeah, so that is it. This particular question, maybe I hope this was clear, but it's just that it's a lot of calculation, so I did not solve it. So apart from that,
What is the final answer for that, sir?
This one, I think it's 1.4, but I have to check again. I think it's 1.4.
Okay, sir.
Yeah, let me just, give me a minute. Let me just check the whatever the answer was given in the solution. I will tell you now itself. Yeah, it's 1.4. Yeah, it's 1.4.
Okay, sir.
Okay, so that is it. If you have any more doubts, you can ask me, or I'll close the session.
Thank you, sir.
Yeah, thank you.
Thank you, sir.
Thank you so much.
Okay, so we'll meet again next Tuesday, same time at 6 o'clock. Thank you
Okay, sir.
everybody for joining the class.